Good afternoon, everyone. My name is Monica, working as Assistant Professor in ECS Department at G. Pullareddy Engineering College. So, today I would like to talk on the topic that is the quantum computing. So, quantum computing is a rapidly emerging field which mainly uses quantum mechanics to perform computations beyond the capabilities of classical computers. So, in this topic, we will be exploring the fundamental principles and also the applications of quantum mechanics. So, in this quantum mechanics, which mainly uses the concept of qubits. So, qubits are nothing but they are the fundamental unit of quantum information. So, whereas the classical computers, which uses the classic bits that is 0 and 1. So, qubits are nothing but they are also called as the quantum bits, which are mainly used in quantum computing. So, in this topic, we will understand the basic principles and also the different applications that have been implemented in the concept of quantum mechanics. So, the next topic is about the building blocks of quantum mechanics. So, the building blocks of quantum mechanics mainly it focuses on the qubits, superposition, and also the entanglement. So, qubits are nothing but they are also the quantum bits. So, it is defined as the fundamental unit of quantum information, whereas the classical computers uses the classical bits, which can be only zeros and ones. But this quantum bits, they can be also simultaneously they can be measured. Classic bits, they are of only the two types, that is 0 and 1, but this quantum bits, they can be 0, 1 or both simultaneously. So which is nothing but it is also called as the superposition. So superposition means the quantum bit exists in multiple states at once until it is measured. Like if at all we flip a coin in the air, it's spinning in the air, so it's both the sides. So it is like both the 0 and 1 that is together, which is nothing but it is the concept of the superposition. And the quantum mechanics, it also focuses on entanglement. So entanglement is nothing but two or more qubits where they are linked, where they become linked, where the state of one instantly affects the others, no matter of how far they are. So it can also be defined like state of one qubit immediately affects the other, no matter how far they are present. So coming to a real life scenario, we see like twins, they wear the same color shirt, even in different cities. If one wears red shirt, the other also does the same. So two or more qubits, they are interlinked with each other. So that is what we call it as the entanglement. So these are the main core concepts which allow the quantum computers to process the information in the impossible ways where the classical machines they cannot perform. So this quantum mechanics, it mainly focuses on the quantum bits, the concept of superposition, and also the entanglement. And next is about the quantum gates. The quantum gates, they are nothing but like the instructions. The quantum gates, they are nothing but they are the operations that change the state of the qubits, where the change of the qubit can be changed. So the change can be performed by applying the concept of the quantum gates. So it is similar to the logical gates in the classic computing. So here we have the different types of the quantum gates, that is the we call it as the Hadamard gate. It is also called as H gate. The controlled NOT gate, it is also called as CNOT gate. And we also use the quantum circuits. So this Hadamard gate, it mainly puts the qubit into the superposition, which allows to be both 0 and 1 at the same time. So superposition means it's like flipping a coin into the air. So when a coin is flipped in the air, so it is present in both the sides, like it's both 0 and 1 together, and that is what we call it as superposition. So this Hadamard gate, it mainly puts the qubit into the superposition, allowing it to be both 0 and 1 at the same time. And next we have the controlled NOT gate. It is also called as the CNOT gate, which mainly entangles the two qubits, changing the state of one based on the state of the another. So where one qubit state can be changed based on the other qubit state. So here we also learn about the quantum circuits. So quantum circuits also play an important role. So mainly this quantum circuits, they use the superconducting circuits. So superconducting circuits are the electronic circuits that work at very low temperature. So quantum circuits, it is also defined as the sequence of the quantum gates, like the recipe, like the steps in a recipe to achieve the final dish. So Hadamard gate, it puts the qubit into superposition, means that is 0 and 1 at the same time. And the CNOT gate, which entangles the two qubits, where one qubit changes depending on the state of the another qubit. So by combining the states, the quantum circuit solves complex problems. So complex problems means like breaking tough passwords, and the molecules for the new medicine can also be found. So quantum computing, it also uses different kinds of algorithms. Those are called as the quantum algorithms. So where the quantum computing is actually brought into the action. So which mainly uses superposition and also entanglement to solve the complex problems much faster than the classical computers. Quantum algorithms, as we all know that algorithms, they are nothing but they define the step-by-step instructions. So in the same way, quantum algorithms also define step-by-step instructions designed for quantum computers. They use the power of superposition and entanglement to solve the problems much faster than the regular computers. In the quantum algorithms, mainly we use the Shor algorithm and also the Grover's algorithm. Shor algorithm is that which breaks down the large numbers into the smaller ones. Mostly the online security is based on the concept of factoring. So Shor's algorithm will do it very fastly, which can break the classical encryption. So the advantages of using this algorithm, the quantum algorithm, is that where we can break the concept of encryption, the drug discovery can be found, so faster searches can be done. So in the breaking of this encryption, quantum computers, they uses the concept of the factoring. The quantum computers can factor large numbers, posing a threat to current online security protocols. And drug discovery, so simulating the molecular interactions for new medicines, accelerating research and development. And we can also do the faster searches, so searching large unsorted databases much quicker than classical algorithms. So this faster searches can be done by using the Grover's algorithm. So Grover's algorithm, where we can search through a large unsorted database faster than the normal computer. So Grover's algorithm does it very faster. So to sort a large unsorted database than the regular computers. So by using the quantum algorithms, all these can be achieved easily. And the quantum algorithms also solve the complex problems much faster than the classical computers. So these are some of the uh, applications: breaking of the encryption, drug discovery, and also the faster searches. And next one is about the quantum errors. As we all know that quantum computers, they are very sensitive. They are highly sensitive to heat, light, and noise, which can cause errors in the qubit operations. The quantum error correction, which mainly uses the techniques to detect and fix the errors in qubits, that is crucial for building reliable quantum computers. And also redundancy. So spreading quantum information across many qubits to protect against individual qubit errors. So surface code is nothing but it is a popular error correction method which mainly arranges qubits in a two-dimension grid to create a robust quantum system. So these quantum computers, they are highly sensitive, and by using this quantum error correction, we can detect and fix the errors very easily. We can also spread across many qubits, and we can also store the information in one qubit. In the quantum mechanics, we also use the concept of the mathematical foundations. So quantum mechanics, it mainly relies on the advanced mathematical concepts to describe the behavior of quantum systems. So here we will be mainly using linear algebra. So linear algebra is that it is a branch of maths which deals with vectors, matrices, and linear transformations, where the quantum states, they are represented as vectors and quantum operations as matrices. So apart from linear algebra, we also use complex numbers. So complex numbers, which are mainly essential for describing the probability amplitudes and also the phase of quantum states, which are usually represented as a plus bi or a minus bi, where we can calculate the dot product. So it is also called as the complex conjugate. And we also use the tensor products. So tensor product is that which is mainly used to combine the individual qubits or the quantum gates into a joint state for the multiple qubits. And we also understand the concept of the probability amplitudes. So probability amplitude is that it is defined as the square of the magnitude of a probability amplitude, which gives the probability distribution of the measurement outcomes. So apart from that, we also use the concept of eigenvalues and eigenvectors. We also use matrices here. The inner product or the dot product can be calculated. We also use the concept of probability and statistics, the probability distribution, and also the probability amplitude. So the probability distribution is that where we can interpret the probability distributions and make sure the outcome is true. So all these are the advanced mathematical concepts which are mainly used to describe the behavior of the quantum systems. So these are some of the advanced mathematical concepts which are used to understand the behavior of quantum systems. And in the quantum, it also uses key theorems, which are called as the key quantum principles. We mainly use the no cloning theorem and also the Bell's theorem. So no cloning theorem is that which makes it's impossible to perfectly copy an arbitrary unknown quantum state. You can measure a qubit, but you can't clone it without knowing the exact state. Like no cloning theorem, it is that we can't copy actually. So it is highly secured. Like the secret recipe is only known to a chef. We taste, but we can't recreate it. Unless the chef tells the exact ingredients step by step, then only we can do the exact recipe. So we can measure a qubit, but we can't clone it without knowing everything. So making an exact copy of files, of programs or data, that is what we call it as cloning. So here the cloning is not allowed here. So we can't copy. So in classical computers, we can easily copy information. But quantum computing, we can't copy it perfectly if you don't know exactly what it is. So that is what we call it as the no cloning theorem, and it also implements Bell's theorem. So Bell's theorem is that states that the universe is stranger than we have imagined. So the quantum particles are deeply connected even when they are far apart. So it mainly highlights that the universe is stranger and it is vast than we have imagined. So confirming that quantum particles, all of them, they are deeply connected even when far apart. And next is about the wave particle duality. So in the wave particle duality, everything has the wave nature. Light particles and the macroscopic objects, the particles, they can also act as waves too. So one way to see the wave nature of light is through diffraction. So diffraction is nothing but bending of the light rays is called as diffraction. The way light bends around the sharp edges of objects or creates patterns when passing through narrow gaps. So in the double slit experiment, a laser light passes through two slits in a wall and spreads out like a wave as it passes through. The waves coming from each slit, they interfere with each other, creating a pattern of light and dark spots on a wall on the other side. This happens when two crests or troughs they meet, they add together. But when crest and trough they meet, they cancel out. So if instead a laser light you throw particles at a wall, if you have a powerful electron beam, you can see instead of two spots directly behind the slits or randomly distributed spots on interference pattern, an interference pattern will appear, just like the light. The electrons are behaving like waves and interfering with each other. So the double slit experiment states that when the particles like electron, they pass through two slits, they create an interference pattern which mainly behaves like waves. Even when sent one at a time, each electron interferes with itself, demonstrating its wave nature. So the next one is about the Heisenberg's uncertainty principle. So Heisenberg's uncertainty principle states that it is not possible to measure simultaneously both the position and momentum of a microscopic particle with absolute accuracy or certainty. So it's impossible to simultaneously measure or to calculate both the position and momentum of the microscopic particle with the absolute accuracy. So this principle mainly focuses or applies to the microscopic particles like the electrons, photons, but is negligible for the macroscopic objects. The more precisely you know one property, the less precisely you can know the other. So the Heisenberg's uncertainty principle, we have the formula that is delta R into delta P greater than or is equal to H bar by 2. So delta R is nothing but uncertainty in position, delta P is uncertainty in momentum, and where H is nothing but it is the reduced Planck's constant here. So If at all the delta x is small, the position of microscopic particle is known with high degree of accuracy. If delta p is small, the momentum is measured accurately. So, no impact on macroscopic level. Next, we have the wave function. The wave function is the fundamental and the mathematical description that holds all information about a quantum system. The wave function doesn't tell us exactly where the particle is, instead tells the probability of finding the particle at the certain place whenever we look at. So, which is represented with the Greek letter, that is psi. So, the probability, it tells the probability and not the position. It does not tell us exactly where a particle is, but rather the probability of finding it at certain place when we look. The Schrodinger wave equation. The Schrodinger wave equation tells that instead of describing the motion with position and velocity, it describes the wave function which holds all information about the quantum system. So the Schrodinger wave equation is applied for both the time dependent and also for the time independent. For time dependent, we call it as time dependent Schrodinger equation, and for time independent, we call it as the time independent Schrodinger equation. So, which mainly governs how the wave function changes over time, describing the dynamics of the quantum particles. And next one is about the discrete energy levels. The electrons in atoms can only exist at specific fixed energy values, forming stationary states or standing waves. So all these can be defined by using the concept of the wave function.